So let's change to presentation. So we'll talk about the design of network topologies using graph invariants. We are from the telecommunications laboratory that's in Vitória, Espírito Santo, in Brazil. So it's just to show a little bit our lab. So here, I don't know how to. Okay. So we have Espírito Santo is a small state in Brazil, and Vitória is an island in Brazil. So our lab is just there, just 25. I could not. Yes? So just 25 minutes with the beach, my food. So this is our good point. So graphs, as you know, is a mathematical structure that is useful to model relationships between objects of a given set. So these objects can be everything you want. So for us, it will be a vertex or nodes in telecommunications and networks. So vertex is a term used in graph theory literature, and in telecommunications we prefer the term node, but it's the same thing. And a network is a set of nodes interconnected by links. So we can, it is immediate to think about a network as graphs. And in the case of telecommunications, our goal with this graph, this model, is to communicate, that is, to exchange data. So we have here the vertex and nodes, and the links that represent the relationships between the nodes. So in this case, that relation is, for instance, a cable of fiber optics or any kind of, even a wireless link. But the point is that if you are able to communicate between two nodes, then we add a link. If you cannot reach these nodes, we do not add a link. So this is our basic plan. So in telecommunications, in order to exchange data, we need to do a request connection. And for that, we need to choose a path. So, for instance, in this small network, if you want to communicate from node 1 to node 3, we can, for instance, choose path A that have 2 links, or path B that have 3 links. In general, we use shortest path to communicate. So in this case, we would almost always prefer path A, just because it has less links than the other one. But it's not always the case. Sometimes we have weight functions, then we can choose the shortest path according to these weights. But in our analysis here, we assume that the number of links is the cost of the path. So we just have to count the number of links. So the problem is that the quality of these paths impacts directly all the upper layers in the network. So this is why we are worried about the physical topology, because everything is limited by the results of the physical topology. So now our talk here will be about the design, particularly focus on the physical part of the network, the infrastructure. So the problem of the network physical topology is given a set of nodes, how to interconnect them. So the network topology is the way the nodes are interconnected by the links. So this is an example, but we would interconnect the same number of nodes in different ways. So the problem is how we should do that if we are network requirements that changing according to the applications. So for a backbone networks, we have a set of constraints. For a data center network, we have a different set of constraints. So we not necessarily should interconnect the same number of nodes in the same way. And this is the problem of designing a physical network topology. Of course, the number of links in a network is related to the cost of the network. But in this case, for instance, we have this topology and this topology. They have the same number of nodes and the same number of links, but we could not expect that they work in the same way. So in different applications, we could prefer this one or this one. So this is the point to use graph theory or graph invariants to choose to design the network topology. Also, even in networks that have the same number of links, if they are interconnected in different ways, so it could impact the fault tolerance, that is the number of simultaneous failures that the network can support before to get disconnected, and also the quality of the signal at the receiver node, because that quality depends on the number of links the signal traverses, and also the resilience, that is how the network behaves after a failure or during a failure scenario. So why this problem is important, or why it's difficult? Because we cannot try every graphs, every possibilities. We have, for instance, here we show the number of nodes, and here the number of connected graphs with this number of nodes. So for instance, with just 7 nodes, that is the examples of this picture. So there are with 800, almost 800 graphs, connected graphs to choose. And when this number grows, the number of graphs grows very quickly. So we cannot try all possibilities. And even if we fix the number of links, we also have a large number of graphs. So for instance, if you fix 15 nodes and 17 links, we also have 800 graphs to test. And also this number increases very quickly. So this is the motivation to design network topologies using graph theory, so you can do some kind of filter using the requirements that your network have. So in order to do that, we have to map the network invariants into graph invariants, the network requirements and graph invariants. So for instance, the cost of the network can be represented by the size, that is the number of links, and also the maximum degree and the average degree. No, the degree of node is just the number of links connected to that node. So then in many applications, the maximum degree is a very important constraint, because it is related to the cost to the physical, to build physically the equipment. For instance, an optical router sometimes cannot has more than 4 links connected to them, for instance. And the cost of this router can be 10 times large if you need 5 links instead of 4. So it's not linear in some applications. The average degree also, that is the 2 times the number of links over the number of nodes, it also is invariant related to the cost of the network. The maximum latency, that is the time to reach all nodes from a given node, that is the diameter is related to the latency, and the average distance is naturally related to the average distance. For the network congestion, that is the number of paths in the same links at the same time, can be represented by the edge between it, or the node between zones, if the congestion is on the node. And the degree variance, because if you have a height difference between the degree of the network, so we could have congestion in that nodes that are at the middle of many of pairs of nodes. For the survivability or the fault tolerance, that is the number of nodes a network can survive before to get disconnected, we use the node connectivity, and the same concept for links, we have the edge connectivity. And for resilience, we propose a new index that is called node Wiener impact, and I will show you as an example of designing new invariants. I will show you how we get to this measure. So the point is, everything here is very simple, and it applies for almost every network application. But if it is not enough, we can just design a new invariant to reach our network requirements. And we did that for backbone networks with this node Wiener impact. And we also did that for backbone networks with the residual mean distance that I will present you this afternoon. So the problem is defined in this way. The number of nodes is the input, so we cannot choose. You cannot say, "Oh, I need a network which minimizes the number of links," but there's no constraint about the number of nodes. I never see them. So we assume here that the number of nodes is an input. And just for example, from that list, we have chosen for first solutions of the network design problem. We have chosen the number of links representing the cost, the node connectivity representing the fault tolerance, and the diameter representing the delay, network delay. So, obviously, if you don't have constraints about the network cost, we could use this solution for the network design. That is a complete graph. Because we should choose that. Because for the same, if you don't have constraints about the number of links, we could have the least possible diameter and the largest possible node connectivity. So we have the network that is the most fault tolerant possible. That is the best choice if the links does not cost so much. But it's not the case, almost never. So that obviously solution will reach the constraints of fault tolerance and quality. That means resilience, but not the cost one. Now we change the other extreme, so here the links costs very much. I have to minimize the number of links, so the minimum scenario possible are the trees that are the connected graphs. If you have any nodes with n-1 links, we can design many kinds of trees. So for instance, on 7 nodes we have 11 possibilities. And among these possibilities, we can always choose a diameter between 2 and n-1. So we have many choices here. Often people use only this model that is a path, or this one that is a star, but to have always a large number of trees to use. And here also the design is interesting because you have the diameter change, the maximum node degree change, the edge between is change, many other parameters such as algebraic connectivity and so on. So this is an interesting problem also. But here, of course, the problem is that the fault tolerance. Every tree can become disconnected by removing a single node or a single link. So it does not satisfy the requirement of fault tolerance. But it do for quality because we can choose, with the same number of links, we can choose the diameter. Also, a solution that many telecommunications engineers likes and applies every day is the cycle-wide cycles, because the cycles are the topologies that use the least possible number of links or resources, and that survives to a single node or any single node or link failure. So here we have this connectivity equals to 2, so the network survives to any single link failure. And use for that only one link more than for a tree. So for any nodes, we have n links. So it is it's not an expensive topology. What is the problem here? The problem is the diameter. If you have a small number of nodes, it's not necessarily a problem. But when the number of nodes grows, so what happens is that even if during the normal operation of the nodes, the network, the signal, the receivers receive a signal of good quality. The problem is that after a failure, the diameter grows from n/2 to n-2 or n-1 after a single failure. So if your network was not designed to that, we cannot, the signal cannot reach the receiver, so we will lose information. Even if the network remains connected after a failure, we cannot guarantee the quality of the signal. That is the problem of the cycles. So these basic parameters that are the node connectivity, the diameter, the number of nodes, cannot help if you don't pay attention to what happens after the failure, what happens with these invariants after the failure. So how can we solve that? First, we have to change the node connectivity for node geodetically connectivity. What does it mean? So to survive a failure, in the sense that the network remains connected and the signal will be received, we have to design a network where instead of just two paths interconnecting any pair of nodes, we have to design two shortest paths, or two geodesics. And that means we have to, the network must have two paths of limited length. I use this D here for this limit. So in this way, if after a failure, we can also reach any nodes within the links. So in order to build these topologies that we will have two geodesics, or two shortest paths for any pair of nodes, we will first define two different invariants. I cannot say that they are new, but maybe these ones, not everybody knows, I don't know. So the first one is the Wiener index. The Wiener index was proposed by Wiener, of course, in 1947 in a paper of a chemistry journal. And that Wiener counts the half sum of the distance matrix. So if you take the distance matrix of a graph, here's an example for the cycle on 7 nodes. So we put for each entry of the matrix the distance, that is the number of links in the shortest path between these two nodes. And you do that for every pair of nodes. Then you sum and take the half part. Then the transmission of a node is just the sum of the distance between a particular node to all other nodes. So you just have to sum a line or a column, a row or column of the distance matrix. And if you sum the transmissions of each node, we have, of course, 2 times the Wiener index. So what happens if we remove a node in this cycle C7? We will see that some paths change, the length of some paths change. So for instance, if we remove this node here, before from this node to this node we have 2 links, and then if this one fails, we have now 5 links to get the same destination. So instead of a 2 in this matrix, we would expect to see a 5. So this is this 5. So here in red, we have the distance that have changed after a failure that is modeled by removing a node. So what we do here is we compute the Wiener index of the cycle, that is 42 for this C7. Then the transmission of a node, that is 11. Of course, all nodes are equivalent in that topology, so I could choose any one. So the transmission, that is the sum of this column, is 12. Then, if we take this new matrix of the C set minus this node, and we compute again the linear index, we will get 35. So what happens here? We show that this node that I have removed, it have impacted the linear index of the new network. So why that? Because I could expect to find 42 minus 12, so I could expect 30 here, but I have found 35. So these 5 are exactly the difference between this 3 and this 4, so 1, 2 times, or 5 minus 2, that's 3. So this 5 is exactly the difference on the lengths of the paths. So the paths have been impacted by this amount. That is the difference between this one and the difference of this one. So it's easy to see the equation. So the linear index, the ideal solution, that is a solution that will not be impacted by removing a node, would be one where the linear index corresponds to the linear index after the failure corresponds to the linear index of the original graph minus the transmission of the graph you have removed. So that difference between these two quantities we will call the node linear impact. That is the impact of that failure on the linear index. So why it will be the ideal solution? Because in that case, it will mean that all distance remains the same after that failure. So that means that we have two geodesics connecting each pair of nodes. So the question now is, are there graphs reaching these properties? Are there graphs where it's possible to do that? And fortunately, the answer is yes. And we have found the first solution using the AGX, because it's French name, software. And this software, if I have time, I can. No, I don't have time, but after, if we are interested, I can show you how this software works after. That is a software that designs a graph from graph invariants. So to get this solution, we have implemented that function, this one, and then we ask the software to find a graph that satisfies that. And it found this solution. The solution has 10 nodes, 21 links, it's two connected, and it has diameter 3. And we cannot see, but here we show the transmissions before and after removing each node, and you can believe these are the same. So this is a graph where we have two shortest paths connecting each pair of nodes, so the distance matrix after removing each node remains the same. So after that, we have found a family of graphs that reach these properties, and that family is called the twin graphs. So here we have all graphs, then the all connected graphs. Apart the trees, we have the two connected graphs. Inside the two connected, we have the two geodetically connected graphs. That is the graphs which have these two shortest paths connecting every pair of nodes. Then we are interested in these graphs that minimizes the number of links, because in telecommunications in general, links represents costs. So the minimum, in this sense here, minimum means the minimum number of links. Then inside this class we have the twin graphs. So what is the difference? Why twin graphs are not all this class? Just for definition from mathematical aspects. We have only two small graphs here. That is the cube graph and the C3. The C3. They are the only exceptions. So we can think about the minimum two GC graphs as twin graphs. So this is an example. So for 7 nodes, the twin graphs are a family, not a single graph. This is an example that has linear index 34, and this graph satisfies these properties. Then all twin graphs on any nodes have 2n-4 links, and they are two connected, and they have diameter also changing from 2, ranging from 2 to n over 2. So here also we have a family that is can be related to the trees, because for each n or each number of nodes, we always have at least one twin graphs with every diameter in this range. So the family is built as the family of trees. And also we studied after that ways to build twin graphs using trees. Some kind of graph operations to get twin graphs from trees. So we consider that as we can notice here, we can choose two nodes, of course, two non-adjacent nodes, because if they are adjacent, of course, there is only one shortest path. But you can try. Try, for instance, this one and this one. You have to choose to find the two shortest path interconnect them. Is it okay? Or if you have questions, you can ask any time. Okay. Did you find? So for instance, from this node to this node, we have 1, 2, 3. Then we can get here 1, 2, 3. So also, when I say two shortest path, I mean disjoint paths, of course, to be sure that the graph will survive any single failure. Okay? So, also to answer the question, are there twin graphs? How many twin graphs there are? I show you here. Here is the number of nodes, and here the number of connected graphs. Here the number of trees on this number of nodes. Then two connected graphs, then twin graphs. So as you can see, the twin graphs behaviors for the two connected graphs as the twins for the connected ones. So also, for instance, for 17 nodes, we have 300 twin graphs. So that means that we can also choose, even if you have this kind of filter, well, I have to choose two n-4 links, so it is very a strong constraint. Then I decided to ask these graphs to have two shortest path for disjoint shortest path for any pair of nodes, and also we can also get at the end 30 graphs to choose from for a network design. So what are the properties of these graphs? For instance, just to show the diameter and the maximum degree. Of course, there is a trade-off between these two graph invariants, but anyway, for this 17, there is always a twin graphs on diameter ranging from 2 to 8 and maximum degree from 4 to 15. So that family spreads and have different characteristics, and you can, from a particular design, you can choose what twin graphs is more interesting for your project. And of course, I didn't talk about twin graphs, but it's a simple example of how to use graph invariants to design a physical topology, and also how to design a new invariant that captures all you need about your network. So here in this example, just the diameter was not enough to our requirements, so I could not ask AGX, give me the graph that has the small diameter possible. It doesn't work because I need the diameter after the failure. So we designed a new invariant to capture this behavior. That was the node-linear impact. So just to compare the solutions, of course, it's a game, it's not a true result. Just to show how to think about this graph invariance as modeling or as mapping your network requirements, then you can compare different kinds of topologies. So this new invariant was called the node-linear impact. Then the node-linear impact is the difference between the two quantities. So here we have a number for each node. Then we can take the average if you want, or the maximum one. Then give that new index for a software such as the AGX. Then now it could solve network topologies problems using this one. Or if you have need all others functions, it was also possible to build the boxes and build a function that represents your invariant. So we did the same for the residual mean distance that has more or less the same idea of removing a node or a link and compute some invariant before and after that failure. And for the residual mean distance, we do that for the average distance. I will talk about that this afternoon. So to know more about this node-linear impact and the linear index and the residual mean distance, I put here the reference of our works. And I would like to thank our funding agents and also people from the clubs for the organization of the SSN. Muchas gracias.